All right, let's take a look. The rate of effusion of gas R is inversely proportional to the root square of its molar mass m. The relative rate of diffusion of two gases is expressed as an inverse of their ratio of their square roots. Well, by this formula here, it's easier to look at than put into words. One thing I would notice is, remember, this formula is the opposite of most ratios. Remember, most ratios would be 1 here, 1 here. Because it's really inverse to the molar mass, as I derived in the lecture, you have diagonal pairings, R2, M2, R1, M1. The most common thing I see going wrong is a bad pairing here. The next thing that causes people consternation is the wording. In an effusion experiment, it was determined that nitrogen gas effuses at a rate 1.82 times faster than the unknown gas. So if we're to write our ratio, we have R n squared fuses 1.812 times the rate of gas X. The molar mass of nitrogen is going to be 28 and change. Where did my periodic table go? My periodic table has run away from me. You can run, but you can't hide. Aha. Let's see here. Maybe. Actually, you kind of can run. Here we go. It's going to be 14.0067 times 2 is 28.013 grams. So now we're going to set up our ratio, where we have the rate of X over the rate of n squared equals the molar mass of X over the molar mass of nitrogen. Plugging in the numbers that we know, and when we plug in, that gives us Rx divided by 1.812 Rx equals the square root of 28.013 grams over mx. Couple things. First, our x's cancel out. So that gives us 1 over 1.812 equals the square root of 28.013 over mx. We have to get rid of the square root, so square both sides. So I have 1.812 inverse, then I square it, gives 0.304557 equals 28.013 over mx. we have to multiply both sides by mx to get it out from underneath the bottom. So that gives us mx times 0.30457 equals 28.013. I have to get my variable by myself now. 30457, 0.30457. So that gives me mx equals woohoo! 91.98 grams per mole. And I was doing 3 sig figs. It really should be 4 because they gave us 4 there. So it really should be 91.98 grams per mole. And that's the answer to part A. Let's take a look at part B. Alright, part B is really a review over empirical formula. They tell us that our formula is 30.45% nitrogen, 69.55% oxygen. So we're going to do our standard assumption. We're going to assume we have 100 grams, which means that we have 30.45 grams of nitrogen, and we want to convert that to moles. 14.067 grams 1 mole. Same thing for our oxygen here. We're going to assume that since we have 100 grams, that means we have 69.55 grams of oxygen. And 1 mole of oxygen is 15.9994 grams of oxygen. So that gives me 30.45 divided by 14.0067 equals 2.17. 396 moles of nitrogen. And for oxygen, that's going to give us 69.55 divided by 15.9994, or 4.347 moles of oxygen. Our lesser number of moles is our moles of nitrogen, so we're going to divide both by our moles of nitrogen. And, oh, that's going to be easy. I can do that one in my head here. Yeah. And that gives us 2 moles of oxygen per every mole of nitrogen. So our formula would be nitrogen dioxide, and that's our empirical. They want to know the molecular formula, so we still have one more step. Let's figure out the formula weight of that. It's got 1 nitrogen, 14.0067, plus 2 oxygens at 15.9994 grams each, for a total of 46.0055 grams per empirical. Then from the last part of the question, we know that there's a molar mass of 91.98 grams per mole. We divide it by our empirical formula, and that gives us, it's going to give us 2, I believe, and it does. So that's our multiplier. So our molecular formula is N2O4, dinitrogen tetroxide.